Hello, everyone. Thank you for joining our webinar. My name is Jake Martinez, Brand Marketing Manager for KP Performance Antennas at Infinite Electronics. Today's presentation will be led by Fixed Wireless Expert and Product Line Manager for KP Performance, Justin Pollock, who will share basic requirements to consider in choosing the right antenna for your fixed wireless network.
Thanks, Jake. So today we're just going to get right into it and we're going to talk about how do you choose the right antenna to maximize your investment. And there's a number of different considerations, but I think one of the most important is understanding your antenna specifications and how they relate to your performance, and then looking at the different application requirements for the antennas, whether it be for access point, user equipment, or backhaul. And then at the concluding, we're going to look at best practices for install. So many different types of antennas, whether it's a sector, a parabolic, an omni, Yagi, but they all have a number of very similar electrical and mechanical properties. Now for electrical, I think some of the most important are the operating frequency band, the beam width, and the gain. And then for mechanical, you can look at the size, the weight, the operating wind load. But all these parameters and properties have a certain definitions in defining um, how they how they are on the spec sheet. So we're going to look at one, I think, the most important and contentious parameter, which is gain. So gain is very important for both the operator and the manufacturer, and it really sets how the antenna performs in the field. Now, gain is an absolute measure of the antenna's focusing power, but it also takes into account loss. So if you didn't take into account loss, you're actually describing a quantity called directivity. So directivity is focusing of an antenna, and it doesn't matter what is the loss. Now, once you take into account the antenna's efficiency, whether it be the material or some other factors, return loss, then you actually making it are defining gain. So here we're just going to kind of just describe what we're talking about. So here we're showing an isotropic pattern with 0 dBi gain, and then you introduce some type of reflector or something, and all of a sudden you can focus the power forward a little bit, and then you have a 10 dBi directivity. Now, once you take into account the material losses of that antenna, so let's say it has some metal losses, you have an efficiency, let's say of 50%, and so the gain drops by 3 dBi to 7. So this is actually what you would see in the field. And what should should be expecting too if someone's defining a parameter as gain. Now, a lot of the times you can see the parameters defined on the datasheet as directive gain, but that would refer to directivity, so it doesn't take into account actual losses. Some other things you can do um, it is how the gain varies across the frequency and how you define that gain. So you can define a typical value, you can define it as the maximum value across the whole band or an average. But you can see here, if you take it as a maximum, there's a very big gain swings at the low part of the band below their expected gain. So really truer definition is actually looking at the min and max value of the gain across the whole band and reporting that on the data sheet, or a tolerance around a typical or average value. Um, so if you're ever calling the question the gain of an antenna, let's say it's vastly off what you think it is, some back of the hand calculations you can use based off of the area, so the surface area of the antenna times the frequency or the beam width of the antenna can get you close to where the theoretical gain of that antenna will be. So you can see here that the definition of gain is going to be setting your expectations in the field of what you expect that antenna to be forming. And if that definition is more favorable to the antenna, then you can be running into issues where it's not performing to your requirements. Now, front to back is another important definition, and really that's going to look at how much power is moving forward versus backwards. So here we see the front to back is, if we define it at 180, it's just minus 40 dB. That's actually very good. But if we're actually using this over two sectors that are front to back that are sharing a channel, frequency reuse 2, you actually care about how much power is going backwards over this arc of plus minus 30 degrees around the back lobe. And if you look at this definition, it's actually 33 dB. Front to back instead of 40. So you can see here this different definition of front to back gives you a different spec, and what you're going to see in the field is actually going to be more based off this stringent spec right here and the one you care about. So cross pole is another interesting specification where it's really just a measure of how much power is in your polarization you want to radiate. That's your green, copolarized, versus how much power is in the polarization you don't want to radiate, which on this plot is the red, and that's called the cross pole. So you want a high cross polarization discrimination, across your entire sector. But a lot of the times the definition of cross pole is only defined at 0 degrees right at the main beam. But like I said, you use this across a whole sector, and you really care about the difference in cross pull across that sector, which is 18. Now 18 is actually really good. I've seen it anywhere down to 10 or 5 dB, and MIMO is still working fine. So just another example of how the definition plays a huge role in the spec that you're going to see in the field. Now, on your access point, maximizing your performance is very related to the spec again and of the gain. So if here on the left, we're showing the patterns of an antenna, and the gain on the datasheet reports 17 dBi. But when you actually go and measure it in the field, the gain was much less, between 8.4 to 13.3. So that gain on the datasheet was probably more of a directive gain. As opposed to here with the KP performance data sheet, where on our data sheets we actually report true gain, and the gain measured is very close to the true gain value. You can see that only one frequency is within 0.2 dB less than our reported gain on the data sheet. So how's this going to impact you in the field? Well, if you went and mounted the antenna on the left in the field, you're going to see some type of propagation map that looks at the top left there, where you have lots of red zones, which means you don't get good coverage, a good signal strength. As opposed to using the KP sector, you have a nice filled in green zone around this town, and you're getting good signal strength because the reported gain is very close to the actual true gain of the antenna. Here's another example here where the gains are reported the same on the data sheet, but once you get in the measurement chamber and measure it, the KP antenna, this is a 3 gig 65-degree sector antenna, outperforms a competitor by 2 to 3 dBi, which is going to pay dividends in the future when you install this. Even though the KP antenna might have an extra $100 to $200 cost associated with it, the KP antenna is going to be able to let you reach farther out. So we see here that we're looking at the coverage zones between, the competitor antenna and the KP antenna, and the KP antenna has a 45% increase in coverage zone. So you're going to pick up more subscribers, and we're assuming a very low density of subscribers. We're still able to show a big difference in our monthly revenue return and yearly revenue return, which is going to more than justify and offset your increased capex costs for buying a higher performance antenna. So you can see here that the higher gain is very key here in the access point side to get good signal strength and good return. Same thing on your subscriber side, gain is very key, but also there's a number of other considerations too, such as the front to back and side lobes. So here we're showing what's going to happen if you upgrade from a small integrated antenna to a 1 foot or 2 foot parabolic. And for the small integrated antenna, you're able to get some clients set up here, but they're all at fairly low modulation rates. They're the ones in the orange here in the bottom right. And you can see the MIMO rates is very low, and you're not able to charge these customers that much because you can't give them very high data speeds, maybe 25 down, 5 up. You really want to upgrade them to a higher data speed and get a more return on investment. You go and upgrade these clients to a higher gain antenna, so a 2 foot parabolic, and now all of a sudden your clients are at least 16 QAM MIMO B or QPSK. And you're able to charge that either $100 or $75 data rate and get your return on investment. You're spending an extra $50 a client to get them set up, but your return is going to be that much more over the long run. So it ends up you get a return on investment in 2 months in this case. Now, this is using just some link planning tools to calculate this all out in the modulation rates. But if you take into account some interference effects, which aren't modeled here, this is going to be even bigger, significant improvement over what you see on this chart. Now, very similar things going to go on for the backhaul point to point and the subscriber side. So the backhaul side, let's say you decide to just start with a small integrated panel, and you're able to get a low modulation rate, maybe 140 megabits per second throughput, and that costs $2,600. Now, you could just go and upgrade to an external dish, so a connectorized radio with a 2 foot antenna, the KP 2 foot antenna here. And you can see here that the gain is about 7 dBi higher, and it allows you to get above your noise floor and your receive levels that much more above the noise floor, so your throughput more than doubles, but you only ended up paying an extra $100 in cost, which is quite significant. return for that little investment. Now you may be wondering, well, the investment to go from a 2 foot to a 3 foot or 4 foot antenna high performance, it's significantly jumping up, and your return, which would be your throughput, IP throughput, is not as significant, but it still is a good jump up, going from 330 to 409 megabits per second, going from a 2 foot to a 3 foot. The added benefit here is that you're going to have that much more noise canceling power if you have interference from a specific direction. So you're going to be able to reduce the noise because your side lobes are that much more lower, going from to the higher size dish. So you can see here that there's considerations both on your just raw signal strength that you're going to get, but also your noise cancellation when you're choosing between your parabolic antenna. Now, best practices for install, I think separation is a very key thing that people get often confused with, and it's not very clear. So rule of thumb, 3 to 5 feet separation, but there's more to it than that. An antenna has 3 different zones: a reactive, near field, and far field zone. The far field's way too far away. That's where we want everything around the antenna to be, our two antennas separated, but that's not feasible. So we usually try to mount in the near field zone, and if we have to, into the reactive field zone. Generally speaking, as frequency decreases, the sorry about that, the near field zone also decreases, and as antenna size decreases, the near field zone decreases. So lower frequencies antennas, you can typically, if you just look at near field zone, you can get them closer together without impacting their VSWR or patterns. But if you're worried about isolation and reducing interference on co-channel plans, you actually want to separate them farther out as you go down in frequency, because the free space path loss decreases. So you don't get that natural isolation just due to space between the two antennas at the lower frequencies. So let's say at 0.9 gigahertz, 900 megahertz, you're going to want maybe up to 7 feet of separation, especially if you have some channel sharing going on between two different sectors. If you can, try to mount them vertically apart. You're going to get better isolation because the elevation beams are more narrower, and you're going to have less impact on the patterns that way. Omnis are also very similar. If you place them side by side, you end up getting ripples in the patterns. So try to separate them out even more than you would sectors. You try to want to put your separation, the angles between the antennas, such that they're in null zones of the patterns, and that'll help minimize the impact on each other, and make sure you optimize your performance. Now, another best practice here is when you're doing an install is your alignment. So first things first is always start with a link planning tool to understand your azimuth and elevation angles and your expected signal strength. That could be cloud RF, link planner, tower coverage, atoll, whatever it needs to be. But you just be able to get the angles and expected signal strength, so you have a baseline. Now, what we suggest is when you're out in the field, use GPS, waypoints, and a gun scope. And that'll help you figure out where you should be pointing your azimuth angles. The gun scope really helps one to avoid using compasses, which can be impacted by a number of different things, such as the iron in the tower, or just the change in the magnetic direction, depending on where you are in the earth. Also, when you're doing the elevation angle, it's very important that you use a digital level and you place it on the flattest part of the surface. On the sectors, we suggest placing it on the back of the sector, not the top. And then on a parabolic, just try to find any flat surface on the back of the 2-foot dish, KP 2-foot Proline dish. Put it on the feed horn itself on the back. Now, when you're doing the alignment, make sure you're directly behind the antenna. And we also have to be very careful here, is in that we don't lock onto side lobes when you're doing a parabolic alignment. The side lobes can be anywhere from 10 to 15 dB down, the first ones. And if you see that when you're looking at the signal strength that it is 10 to 15 dB down, you probably are locked onto a side lobe. Now, there's a number of different alignment tools on the market to help you with this, but not everyone needs to use them if these follow these key guidelines that I laid forth right here. So these are the kind of the considerations you need to maximize your antenna investment. You got to realize that your antenna field results may differ from the data speed data sheet specifications. So understanding how the specifications are defined on the data sheet is very key to making sure you optimize your performance in the field. Now, another thing to consider is even if it's only a 1 to 2 dB higher gain in your antenna, it'll allow you to go up to that extra higher modulation rate above that noise floor and increase your revenue and your quality of service. So another key thing here is also make sure you perform propagation studies before you get out in the field to improve your chance of success, and also set your expectations. It's very disheartening to see a signal being much lower in the field than you expected it to be, and having to go back and replan and probably go up and climb the tower again and tilt it. So last is follow our recommended guidelines on the separation, 3 to 5 feet in general, and the alignment is very key to get it right too.
Thank you, Justin, for sharing insights into antenna selection requirements for fixed wireless communication networks. To our audience, we'd like to thank you each for your time and hope you have found this webinar informative. If you have additional questions or like further information on fixed wireless communication networks, please contact us directly to speak with a member of our technical support team at 1-855-276-5772 or visit our website at kpperformance.com.